Okay, welcome to Let's Get to the Marks. We're looking at organic analysis, infrared spectroscopy, and H1 NMR, A-level chemistry. Questions about spectroscopy. Compound K has the molecular formula C4H8O. Figure 1 shows the infrared spectrum of K. We've got the transmittance percentage along with the wave number at the bottom. This is for the IR spec. Which functional group does K contain? Well, we can see there's a peak roughly at 3000. So let's check this out, see what this could be. Bearing in mind we've got the formula C4H8O, could it be a carboxylic acid? Well, no, because carboxylic acid needs two oxygens for the COOH, so that's unlikely to be what it is. The 3000 is probably just for a CH bond. But we've got one about 1750 here, and you can see here that's going to be the carbonyl group. And does that fit our formula? Yes, we could have a CO bond because it just needs one oxygen. So it's going to be carbonyl. Nitrile and amine both have nitrogen, and our molecular formula doesn't contain nitrogen. Right. Let's move on and look at the next question. So we're looking at compound L has a molecular formula of C4H7NO. Figure 2 shows the infrared spectrum of L. I've got the repeat of the question, the stem here. And we've got figure 2, which shows the transmittance and the wave number again. We've got the infrared spectrum up there. So L reacts in the presence of a nickel catalyst to give compound M, suggests three ways in which the infrared spectrum of M is different than this infrared spectrum of L. So they're asking us about a reaction with hydrogen and a nickel catalyst. Now you kind of have to know this off by heart to get this question. So if you've been revising your A-level chemistry, you should know that nitriles react with hydrogen in the presence of a nickel catalyst in industry to form amines, primary amines. And that's what you get here. And now there's no easy way about it. In organic chemistry, there are absolutely tons of mechanisms and organic reactions you have to know off by heart. There's no real easy way about it. You've got to make revision cards and get revising and memorizing. I use CGP revision guides. There are different revision guides, like Pearson's do a decent one as well. And there are other revision guides. I kind of use the CGP. It's just a personal choice. So I'll memorize this information from here. And this is the this A-level content comes from the Chemistry AQA CGP revision guide. Okay, so here you can see down below on this bottom part, it shows you a nitrile with a nickel catalyst, high temperature and pressure becomes an amine. So that must be the reaction they're talking about in our question. You can use lithium aluminium hydride, LiAlH4 above, but that's done in industry and is very expensive. Yeah, that's done in the lab. Right. Anyway, there's two ways to hydrogenate a nitrile. And why is there an oxygen in this? Well, it's probably a hydroxynitrile or something like that. The NO might throw you off. Yeah. So what would be the difference? We're going to make an amine. You can see there's a peak around 3,300. But we've got a peak, which I'm going to show you in a second, at about 2,220. And that is the evidence that we were dealing with a nitrile. If you didn't know that reaction off by heart, you could look and go over here and you see this tiny little sharp peak here. This comes down to about 2,250 or something. And this corresponds with the peak for a nitrile. So if you didn't have that off by heart in your head, maybe you'd recognize that and you'd be able to go to your data book and say, oh, it's a nitrile. Now, we would expect that to disappear when it becomes an amine. So we'd expect this peak here, which we've just shown you, we'd expect that to disappear. And I would expect an appearance of a peak where an amine is for a primary amine. And where's the amine peak on this data booklet? It's right at the top here. So I'm expecting some sort of peak around 3,300 to 3,500. We should see a new peak form. Okay, so some of this information you can get from the data book. And then let's whack all of this down. So what we would say is we would expect the fingerprint region to change. So we'd expect the functional groups to change. That's going to get you a mark, the fingerprint region. And we'd expect the peak for the nitriles to disappear at 2,250. And we'd also expect a peak for an amine to appear at 3,300. Right, let's move on to the next question. Figure 3 shows H1 NMR, that's proton NMR, spectrum Q with a formula, molecular formula of C3H7ClO. Now, my first thought when I see that kind of formula is, oh wow, we're dealing with an acyl chloride, easy peasy. But if you draw out the structure of the acyl chloride, notice there's only 5 hydrogens, but our molecular formula has 7, so this can't be the correct answer. So let's get down to the proper data to work it all out. And bear in mind that if you can just explain the data and you can't deduce the final formula, you still get 4 out of 5 marks. So first of all, we have the chemical shift values. We've got 3.95, 3.65 and 3.35 circled here, and there's their peaks. We then have an integration trace, 0.6, 0.6 and 0.9. What does the integration trace tell you? The integration trace tells you the number of hydrogens in each region. So we've got 3 hydrogen environments, and the hydrogens must be split in a ratio of 2 to H, 2 hydrogens to 2 hydrogens to 3 hydrogens. And I'm going to show you how I work that out. The integration value is actually a ratio. So I just need to put it into whole numbers. So divide all by the smallest, 0.6 by 0.6 and 0.6 by 0.6 equals 1, 0.9 by 0.6 equals 1.5. Times them all by 2 to get them into whole ratios, and you'll come up with the ratio of 2 to 2 to 3, which equals exactly to our 7 hydrogens, which means I've got 2 hydrogens, 2 hydrogens and 3 hydrogens in 3 different hydrogen environments. The chemical shift will give us the potential groups and atoms in each of those environments, and the splitting pattern will tell us how many hydrogens are next to them. So let's look at the chemical groups first of all. And our first one was 3.95. It can't be, so it's only going to be this halogen, a halogen attached to a CH2 group. So if we go to 3.95, so you just need to get the marks right. 3.95 is the chemical shift. The group is this halogen with a CH2 attached, and the integration trace will tell us the number of hydrogens in that environment. So make sure you comment on the integration trace, you point out the group with the chemical shift, and then you comment on the splitting pattern. That's going to score you a mark. 3.95 shift suggests this halogen attached to CH2, and the splitting pattern is a triplet. You can see from the 3 lines. That suggests that the adjacent region is a CH2 group, or a carbon with 2 hydrogens and something else attached. So let's put all that information together to write what we've got so far. We've got a Cl attached to a CH2. Adjacent to it, because of the splitting pattern, is another CH2. So that's what we know so far. Quite a lot. Let's look at 3.65. Well, it's not going to be another halogen because we've only got one of them in the molecular formula. So it must be this ROC with the H. The black H in bold on your wavelength, the one I've circled in orange here, is the one we're looking at. And what's attached to it must be an O with another H. So I've added that to my structure down below. And the splitting pattern of the 2H is just saying that adjacent to it, because there's a triplet splitting pattern, again, another triplet splitting pattern, is saying adjacent to it is a carbon with a CH2. So that's why both of these regions, 3.95 and 3.65, both had triplets, because they're both next to each other and they both contain CH2. So those triplets tell you what's next to each other, and that means we know there's CH2. So finally, let's look at the final chemical shift, which is 3.35. Now, if we look at 3.35, it's not going to be a halogen, so because we've only got one of those, but it could be ROC with another H. And that will be because it's pointing out the same O we've got in our second environment. So what I need to do is flip this diagram around for this group. You just need to point out what it suggests, and it suggests a C with the H and the O and an R group. And the R group is actually the ClCH2CH2. And then on the other side of the O, we're looking at a methyl group. Why is that? Well, we know it's got 3 hydrogens from the integration trace. So it must be a methyl group connected to an O. And the reason it has an R attached on the other side of the O, that's the rest of the molecule that we already discovered. The splitting pattern is a singlet. That tells us there's no hydrogens attached adjacent to the group responsible, and it's a methyl group attached to an O, and an O has no hydrogens attached, hence the singlet. Now, you don't need to name this molecule. I put the name up there, but it's not on the spec. It's an ether. But you do need to draw out the structural formula or display formula, and you can get 4 marks just explaining each stage. And there we go. Hit the
You're
like.
still here?
Let's get to the mark.
It's over.